problem of hydrodynamic limits is the derivation of macroscopic partial differential equations of fluid mechanics from a microscopic description of particles. This type of problem has its origin from David Hilbert's sixth problem with title, The Mathematical Treatment of the Axioms of Physics. This was one of the 23 mathematics problems Hilbert posed in 1900, and it's one of the 8 Hilbert presented at the International Congress of Mathematicians, which held in Paris in 1900. In Hilbert's exact words, thus, Boltzmann's work on the principles of mechanics suggests the problem of developing mathematically the limiting processes there merely indicated, which lead from the atomistic view to the laws of motion of continua. However, there is a little ambiguity in Hilbert's formulation of the sixth problem, in the sense that the term atomistic view in his formulation nowadays can lead to at least 3 very different theories. The first of which is molecular dynamics. Molecular dynamics is the n-body problem of classical mechanics with elastic collisions, in which for simplicity, the bodies are assumed to be spherical and possessing equal mass. The second is interacting particle systems. These are spatiotemporal stochastic processes used to describe the evolution of particles under some kind of interactions between them. And the third is the kinetic theory. And like I said, in this work, or in this talk, the interest is on the derivation of the compressible Euler system of equations from the classical kinetic theory of gases. That is from the Boltzmann equation of the classical kinetic theory of gases. The formal derivation of the compressible Euler equations is given in the following theorem. For epsilon greater than 0, let f epsilon be a solution of the scaled Boltzmann equation given below that satisfies the local conservation laws of mass, momentum, and energy, respectively given as follows. Then in the limit, as epsilon tends to 0, f epsilon converges to the local Maxwellian, where the parameters n, u, and t solves the compressible Euler system of equations, which is given below. Now, proof. Multiplying the scaled, that is the hyperbolic scaling of the Boltzmann equation, by a test function psi, and integrating the resulting equation over all possible values of the velocity variable, we obtain the following equation. This equation is often called the equation of change or the equation of transfer. Now, setting psi to be equal to the mass, components of momentum, and kinetic energy, respectively, in the equation of transfer, gives the local conservation laws of mass, momentum, and kinetic energy, where we have used the fact that the mass, momentum, and kinetic energy are collision invariants to obtain the vanishing of the right-hand side of the conservation equations. Next, observe that multiplying both sides of the hyperbolic scaling of the Boltzmann equation given below by epsilon gives the following equation. Now, passing to the limit as epsilon tends to 0 in this equation, we obtain that the collision kernel, the collision operator vanishes. Then from the H theorem, we must have that F is a local Maxwellian. Furthermore, passing to the limit as epsilon tends to 0 in the local conservation laws given below, we obtain the following limiting form of the local conservation laws. Now, to obtain the compressible Euler equations from the limiting form of the local conservation laws, all we have to do is to substitute the Maxwellians, that is the distribution function, which is of the following form, into the integrals in the limiting form of the collision conservation laws and evaluate them to obtain the following. If you evaluate this integral, you get rho, which is equal to m times n. If you evaluate this integral, you get rho times u, and so on. Upon substituting these expressions into the limiting form of the local conservation laws, gives the compressible Euler system, which is given below. And this in particular concludes the proof and also the end of my talk. So questions, comments, and queries are welcomed at this point. And for more information about the Boltzmann equation, this book is a very good introduction to the Boltzmann equation for the single species and also for multi-species, and the pioneering works on the derivation of hydrodynamic models from the Boltzmann equation are given by this paper and this paper. In particular, this paper dealt with the formal derivations, and this dealt with the convergence proofs. Thank you for your attention.